be removing the mask mandate? Did you?
I haven't heard that.
No. Okay. Well, don't say it yet until it's confirmed. I'm sorry I'm late. I've been running around with And the other thing I want to level with you, I've got your quizzes, everything in your homework in my car. I ran in here and I will go get them and come back. So I got a 2:30 appointment today, and I got to teach a class after this. But if you want it, I'll bring it back in, and I'll bring them all Monday, one of the two. And the last quiz, just so you know, the last quiz we took here, 4 to 5 people got perfect scores. A bunch of them did pretty good, and there were a bunch of people who had a very hard time. And it's happens every semester in here. You get people that really get it, and the further on we get, especially in the final, they just blow it away. And then you get people that, unfortunately, for whatever reasons, and I don't know, they just get further and further behind, and on the final, they just do horribly and they flunk. And I'm trying to encourage you, don't be that person. Do well, study hard, because it gets more and more penalizing the further you go in this course if you don't keep up. I'm just leveling with you. Okay, so I got that. And I got that. Now, today, any questions before I take off on a lecture? Yeah.
Would you mind working homework problem 2?
Yeah, did you all get my message about that was on me? I think it was, John, you're the one who pointed that out, and I think I corrected it, didn't I, class?
Yeah.
We're gonna do this one. This is a good problem too.
Oh, mine's about the choke, not about the choke.
Oh, the choke. Okay, my bad. Then we'll do the choke.
Oh, okay. It's the
It's
the one with
I'm just
the-
gonna put it like this so we can do it.
it's the voltage source and then the resistive load, and it
Oh.
asks you to find the loaded or the voltage of the resistive.
Yeah, isn't this like L?
I don't know if you're trying to look on with me, but
Yeah,
you
it's
have it right there.
37.
And the mutual is,
27. And the resistor is 1 kilo ohm.
what's that?
The resistor is 1 kilo ohm.
Okay. And this is a load voltage, this is R equal 1K, and they want this V out, and they give this, now here's the thing, the original one I try to point out to you that the answer in the book is wrong. All right, the magnitude's right, phase is wrong. Y'all get that class?
Yeah.
Just curious, how many did? You understand? The solution, it's an understandable error when you see what happened. They made this 10 times the sine of omega t, right? And here, F was it
100 megahertz.
100 megahertz. So that means omega is 2 pi F. Now, we don't do these things in the time domain. We're going to go to the frequency domain. We're going to put a phasor representation. So the whole idea is knowing the representation of the sine correctly. They didn't do it right when they did this problem. Normally, you're used to seeing any number when they have a cosine of omega t plus the phase angle just being given as a in the phase angle at a constant frequency. But that's not what we're going to do here. We have to get it in terms, the cosine in terms, the sine in terms of a cosine. And you know that sine of theta is equal to cosine of pi over 2 minus theta. You probably know. I mean, if you don't worry about it. But the whole idea, and the way I always tell people to do this, in case you're wondering, whenever you see trig functions, you're wondering, well, what do they look like in a phasor domain? Always come over here, or the relationship between sine and cosine. If you were plotting omega t and you're using cosine of omega t here, it would look like this, right? I'm just showing you. What about sine? Isn't this a sine? You can see the relationship is 90 degrees, correct, class? Now, you can write this several ways. The cosine is an even function, so I can write sine of omega t, which is like theta here. It can be cosine of pi over 2 minus theta, because sine's an even function. I can multiply that by a negative sign, and I can say that's equal to cosine of simply theta minus pi over 2. Y'all follow me? I wanna make sure you all see this. With me on this class, it's subtle. And here's what usually happens. People would completely ignore this information. And then you take a course in communications, 400 or 500 level course, that requires the phase to be critical because it's phase shift keying, or it's using phase as a reference for like a modulation, FM or something like this. And then it becomes critical, you know, how to do this. So what I'm going to do is say, since this was tan sine of omega t, now I'll slow down. I can just write this as 10 times cosine of omega t right here, and it's gonna be what? Minus pi over 2. Do you all agree with that? Now we'll go to the phasor domain and do this one. The only trick was that, to be honest with you. It's just that voltage source. So, what does that circuit look like in the phasor domain? Appreciate we get rid of that. Oh man. I usually bring a whole bunch of markers down when they leave, but that's not when they stay put. All right, so it looks like this. In the phasor domain, you have plus to minus. The magnitude there is 10, right? And the angle is minus pi over 2, or minus 90 degrees, if you want to do it with degrees volts. Do y'all agree? Now, next I put the equivalent circuit for that choke. The only thing I'm going to do is replace this coil with a simple L minus M. Does everybody understand why? That's the only thing I'm going to do. So this has an inductance of L minus M. And likewise, below it, it has an inductance of L minus M. And then I put down the resistor here, and that R is 1K, and this is V out. Now I didn't do this, but I'm about to. L minus M is not the inductive reactance, that is the value of inductance, equivalent value. So we multiply that by J omega. Y'all with me? You asked this, right?
Yes, sir.
All right. So if we multiply this by J omega, and this by J omega, you can see really we have two of these in series. Yes?
Do we know that's L minus M because it's the common mode chip?
It's in the differential mode is the key. Good point. You all see how currents are going down this way and back this way because it's driven in a differential mode? How many see that right there? All right, if it was common mode, then you would tie these two terminals together and the source would be here, it'd go to ground. You all follow me on that? That would be common mode. Frankly, the only thing we really care about is we want to see what we want to make sure that this works. We want to find the output voltage here. But in common mode, usually what you want to do is contrast common mode output voltage occurrence to differential mode output voltage occurrence. That's a little further down the road, that's in the EMC class. I don't dabble here because it takes a little too much time to develop that. And we'd have to go through rectification, everything like that to show you some more stuff that you need to know. But here, this is a fair circuit right here to understand. How many have taken the FE exam? How many plan on taking it? And I encourage you all to take that exam. The fundamentals in engineering used to be called the engineering training. Now, here's the deal. You're just getting out of college. You know the stuff as well as you're ever going to know. The test is comprehensive. It deals with physics, chemistry, mathematics, and then it goes the second half. It's an 8-hour test. In the morning, it's all basic stuff like that. In the afternoon, it's specialty. If you're an ME, you get a different test than if you're an electrical and computer engineer. You get a specific test. But passing that as soon as you get out is good because you don't know it. But down the road, I mean, there's at least one person mentioning thinking about a career as working as maybe an administrator in an electrical or as an electrician or somebody who did large-scale power grid layouts and stuff like this. They'll need that license. If you're going to work on anything that is related to the power grid or buildings power and stuff like this, you'll need a PE license. Y'all understand that? Now I've got a second-class FCC. I don't have a PE stamp from Alabama because my work is military in nature, and that's really mil-spec stuff, And there's nothing I need a stamp for, because they verify it. I don't have to. They're gonna make sure what I say works the way I said it, or else I don't get paid. Anyway, coming back to this thing, if we want V out here, how do we get it?
Voltage divider?
It is a simple voltage divider, isn't it? Isn't that right? You asked about this, make sure everybody sees this. So for this one, I can say that output voltage, I'm gonna get it in the time domain too, but I wanna get it in the phase domain. The output voltage would be what? Input voltage, right? How can I render that another way, anyway? Just minus J, right? Can I just put minus J in front? Just minus J 10 volts, and then it's gonna be R, or 1,000 ohms, over 1,000 plus, and this would be 2J times omega, which would be 2 pi times 10 to the 8 here, times L minus M, and what is that? That's 3 microhenries, is it? Y'all follow me on that, guys? How many see this right? It's straightforward, but now give me the answers you get. Can you see it, guys, in the back? Clay, far back? Very back quarter. Okay.
2.564 and angle of negative 165.144.
And they go what?
Negative 165.144.
All right, I think that is the right answer, because I put that up. I want to make a statement. What they did was this. They got rid of that minus J. It's 90 degrees out of phase. That's the only difference. Y'all follow me? Does that answer your question?
That was what I missed, was the J.
And I want to tell you, I don't try to trick you at all about that. In the stuff we do, 99% of stuff we do in fundamental, and really the beginnings of electromagnetic applications, antennas, radar, all that, we don't care about the phase. We will care about phase, you will care about it in your comm courses and in true radar work, you need that. But for this stuff, it's really just magnitude of signal. All right, other questions? That's a good one.
Wait, what?
Uh-oh.
What was the answer?
Here, I'll put it up again.
I think I
V out was 2.56 at an angle of minus, say that again, 150 what?
165.
165
So everybody knew it except for people.
degrees volts.
Yeah.
Will we ever have to solve for the M value, or is that going to be given to us?
Damn.
It could be something where if I hook them one way, I got an impedance, and I hook them another way, I get a different impedance, and you could solve for that if you understand with the differential with the common mode. But I'm not gonna ask you to, I don't think you mean this, but
You gave us a
I'm
homework
gonna give
like that.
you a drawing of a slate, and a doctor, and you estimate. Yeah.
Could you run through number 3 real quick?
Yeah, and that's the one I put the corrections for, right?
Yep.
Did you also correct it on the OneNote?
Didn't I? Is
Yeah.
it?
Okay. I knew you sent the email,
I
but
think it's correct.
It is.
Now, if you need to refresh, sometimes my thing doesn't sync automatically and I
Okay.
forget about it. So you may have to sync those.
I keep that page open too. So.
Good luck before I forget to tell you. And what's the line in the game, anybody?
4.5. Auburn. Yeah. You think they'll cover the spread?
Don't ask me. The only thing I get is hate mail, no matter what I say. Every once in a while, I'm just very goofy, maybe somebody says, you need to listen to Feinberg, because there's gonna be some callers, you know.
Always.
All right, who's calling in, they'll tell me. And I know what they're gonna, it's just, it's a circus.
Uh-huh.
They're not serious about anything, they're just saying stuff to provoke a response, and then they get people calling in mad.
He wouldn't do that.
Oh, gosh. I'm getting sick of the Georgia fans.
Yep. Always sick of the Georgia
I live in
fans.
Georgia now.
Oh, I hate that for you.
He's just heavy.
So now for this one, it's a thin shield, right? Might as well pay attention. Hint, you might as well pay attention.
No.
One more time. Hint, you might as well pay attention. Here, this is what? Stainless steel, right? So it's
1040.
thin. So sigma is equal to 5.8 times 10 to the 6. Sometimes I can say it 3 times, and it's like, well, he never mentioned it. Okay. I'm not kidding about that either. And you don't believe me, I'll show it to you. All right, mu relative is 1,000, right? Now, F, help me out, is that
100.
what?
100 megahertz.
100 megahertz, imagine that. 100 megahertz. Thickness D is
Micrometer.
10 to the minus 6 meters, 1 micron, right? Then here's sort of the way it works. Incident field, transmitted field, and there'll be an incident power density, or E incident, and there'll be a transmitted power density, right? So what do they give you? By the way, this is one of those problems. I can give you one of several things, and you can get all the rest. Y'all follow me? But I have to give you the frequency, right? Because that's important. Now, where do we go from here? Not the usual suspects. How about some of the quiet ones? Go ahead.
We solve for alpha.
All right, but there's some, yeah, how do we solve? Very good. How do we solve for alpha? Matter of fact, let's solve for gamma, which is alpha plus j beta. What's that equal to? Square root of j omega mu, sigma plus j omega epsilon, right? I'm going to make a point here, and that's the reason I did this. Y'all agree with me? What's the one thing I'm going to look at before I just brute force everything anyway?
It's a good conductor.
See if it's a good conductor. So sigma is pretty big. What, epsilon relative is 1, right? So what's omega epsilon relative?
Small.
Epsilon relative epsilon naught. Well, that's 2 pi times 10 to the 8th, right? Times epsilon relative 1 times an epsilon naught. You might as well do is 1 over 36 pi times 10 to the minus 9. Now just take a look at that for a second before I ever run that. Y'all follow me? I just multiplied epsilon naught by omega by epsilon relative, correct? And what I'm after is this a lot smaller than this. And if it is, I ignore that because it's a very good conductor. With me? Go ahead.
Can you repeat that?
This is omega epsilon right there, okay? Now, if it's a good conductor, omega epsilon is much less than sigma. You agree? So we're going to investigate that. I've got sigma. So I want to see what this is. Well, omega is 2 pi times f, 2 pi times 10 to the 8th, right? And the only reason I put in the 10 to the minus 9th over 36 pi, I can see a lot of cancellations, and I don't have to run it on my calculator. Y'all see this, class? And if you do, what do you see happening here? 2 pi 36, right? 1 over 18, right? That times that is times 10 to the minus 1, right? Without going a step further, does everybody see that's much less than this? All right, therefore it is a good conductor. Agreed? Now, because of that, alpha equals beta in magnitude, right? You can look here, and that's square root of j omega sigma, so it's going to be 1 plus j over the square root of 2 times that omega mu sigma. And I'm trying not to waste time, but I'm getting to the point. Y'all agree with that, class? You look suspicious. Are you okay? Some people, he's talking fast. He's got to be trying to sneak one by. No, I'm just trying to say for a good conductor, that has to be the case, right? Now, we know, and therefore, and I can just do it right here, alpha is equal to the square root of pi f mu sigma. And that's 1 over skin depth. Can you give that to me? Thank you.
1.487 times 10 to the 6th.
10 to the 6th?
Yes.
By the way, that is large. Radians per meter. It's an enormous amount. All right, so that's alpha. We've got that done. Now we need eta of the shield, correct? How do we get eta of the shield?
Just j omega mu over sigma plus.
I'm gonna just stop and make sure everybody understands that. We're gonna use the fundamental equation, then I'm going to reduce it to the dq. Okay. So it's gonna be square root of j omega mu over sigma plus j omega epsilon, right? Now, based on the last thing we talked about, this is much smaller than this. Y'all follow me? So I'm going to, out of politeness, get rid of that, so it won't irritate. Agreed? What do you get for magnitude and angle? If you just want to give me real and imaginary, they'll be the same, but I prefer magnitude and angle. It's 45 degrees, isn't it? So what's the magnitude? Anyone? Come on, guys, help me out. You got calculators. I'm not trying to.
0.268.
0.368.
Say again?
0.368.
Anybody confirm that? All right, now that's small compared to an 8 and up. We know 8 and up for the atmosphere is 120 pi ohms or 377 ohms. That's much, much less, right? You all agree with that? Now, I'm gonna go ahead next and just get the transmitted field directly from the incident field. And the incident field, in this one, I believe is 10 volts. Is that right?
Yes.
So, I'll slow down for this, make sure everybody catches me. I'll do it right there. So now I know the transmitted field will be equal to, and here's what I need. I need the transmission coefficient at region, I call this region 1, it's the first interface. And I'll call this region 2 the second interface. Y'all with me? By the way, I gotta ask this question. I've never done this to a class before. Has anybody ever called in a sports program before on the radio? You have, I don't wanna ask what you asked. Which one was it, if you don't mind?
It was the Paul Baum show.
Did you get in?
Oh, yeah.
Oh, yeah.
How did I miss that? I know a few people that have called in and they have had a ball, but I'm usually not privy to it. They have to give me a record of it, like a recording. I hope you have a recording of it.
I have a picture of it.
That's even better. Because I know people that go and they troll these people. I mean, really troll them, and they have a ball. Basically,
I'll tell you what I asked him about it.
nothing is gonna be.
No.
All right, what did you say?
Well, it was when Auburn was hiring their athletic director, Alan Green. I asked him what he thought about it.
And what did he say?
He said he didn't know a lot about
Wide open, fresh. He could have had a ball with that. I heard he was a linebacker for Iowa. Say something like that. I don't think I got the wrong guy. He's a baseball player, so good. Go ahead.
So you mentioned that you could give us like a different value than what you did. So like you gave us EI in the homework problem, but you could give us like P-tran.
Sure. Any of these things, you can get all the others, right? If I give you transmitted power, transmitted E field, incident power, incident E field, you can get everything else because of these equations I'm about to show you. All right. Boy, now you got me thinking. All right, so what's the transmission coefficient right here? I did call it once. It wasn't his show. Go ahead.
2 times eta shield.
2 times eta shield, right? Over eta shield plus eta naught. What do you get for that? Why you calculate now? I'll tell you what I called it about. Years ago, we had a coach named Tommy Tuberville.
No.
Tommy beat Alabama 6 years in a row. Tommy got fired because of something. Now he's a senator. Maybe he'll fire some of these people. But anyway, Tommy Tuberville went and he won a game in a bowl game against Virginia Tech. It was down in New Orleans. He beat them. He was undefeated. But there was another team called UCLA. Or I'm sorry, if it was USC, who had Reggie Bush, who got the title. And there were a lot of angry people. So I was feeling fine. I was jammed in traffic, so I called this number and I got in. And now I'm on the radio. What would you like to talk about? Well, I'd like to talk about justice. You gotta hear this. Anybody's ever heard me get in front of a camera? I enjoy this. I mean, not this kind. Well, what kind of justice? This is long before social justice. So, well, Auburn's obviously wrong because of the fact that they're just a good school. They don't cheat. Woo. What do you mean wrong? Well, we're undefeated, untied. Tommy Tuberville beat Alabama 6 years in a row. It's unheard of, right? And we don't even get a share of the national title. Man, you want to talk about throwing a match on gas. The calls come, how can that moron say? And you know what I'm talking about, if you know anything about football in this state, but that's just basically burning down the barn. And the barn did burn down. I'm not lying about this. Does anybody know this?
Yeah.
Oh man, it gets crazy. All right, what do you get for that?
0.002.
At 45?
I didn't know the barn burned down.
Yeah.
All right, man, now, the next thing I need is what? I need Tau 2, right? How many know what Tau 2 is gonna be, just by looking?
That's crazy. I'm gonna have to look that
It's
up.
gonna be about 2, right? It's equal to 2 times eta naught over eta naught plus eta shield. Since eta shield is so small, this is about 2. And now we go right in to get the transmitted E field. I don't know why on Friday, a lot of crazy stuff going on right now. Anyway, I'm just in a decent mood for it. Anyway, come down here to get the transmitted E field's magnitude. Well, first start with the incident E field, which I didn't before. And I think John Short, was it you? You sent
Thomas.
me, or Thomas, sorry.
Yeah.
You're the first guy to notice, but other people did too. So how come you didn't include the E field? Because I was stupid. Anyway, the incident E field goes here, so I'll put EI here, magnitude. Next, I take the transmission coefficient, goes from free space to region 1. Then the second transmission coefficient, layer 2. And then what do I have to do? I have to take exp to the minus alpha times the thickness, right? Isn't that right? And that would be the transmitted field. Now you'll notice that this doesn't depend on the field at all, just the frequency, right? And materials and thickness. It's separate from the field. So if I give you transmitted field, you can get incident. If I give you incident, you can get transmitted. All right? What is that, by the way?
9 millivolts.
Say again?
I think it's 9 millivolts.
Is it 9? We'll just care about the magnitude. So it's 9 millivolts per meter is the electric field strength. Real quick, how do you get the power densities? What is the incident? First, let me do this. Are there any questions about this? Okay. What's the incident power density? It's always going to be of this form, right? And technically, if I wanted to be exact about this, what I would do is this. This is something for the future. Write this down for the fun. It would be the magnitude of the impedance that you're going through, and then there would be the cosine of the angle associated with that impedance. Y'all remember that class?
Mm-hmm.
Now, if cosine squared, pardon. No, just cosine angle, my bad. Just cosine the angle. And here's why that's important, because if you're in a good conductor, it'll be cosine of 45 degrees, which is 1 over square root of 2. Now just keep that in mind for the final. I may even remind you of that on the final, but there's usually a problem related to that. And here's exactly what I know what people are thinking. Why is he saying that? Suppose I wanted the power density, listen to me, just after the field gets inside here, how would you get it? Do you all understand the question? Mm-hmm. Field's coming, some of it's reflected, a little bit transits, that's right there, right? The magnitude of that would be transmission coefficient times incident field. But what would the power density be? It would be one half the E transmitted here squared, right? But then it would be divided by magnitude of the shielding impedance times the cosine of 45 degrees, and that's important. I just outlined what you need to know. Do y'all follow me on that or not? You're looking at me like I said something wrong. What did I? You good with that? Yeah.
So you're saying for this problem, the kind doesn't apply, like for this kind of?
Why doesn't it, class?
Because it's not instantaneous.
I'm not asking for anything inside the shield, right? I'm asking for the free space or the power density for the transmitted in the incident field where it's what? 8 is just strict real, is it? Y'all with me? Okay, good. So for the power densities, that's it exactly. Here. This is what it would be, and this would be incident, what is that? I think it's points 3 something, I don't remember exactly.
0.133.
Is it 0.133?
Mhm.
Watts per meter squared. What about the transmitted power density?
Mm-hmm. 1.07 times 10 to the minus 7.
I think that's it, right?
Shield effect.
And shielding effectiveness, you don't need E field for that. Shielding effectiveness is what?
20 log.
20 times the log. We know it's going to be positive, so if you get a negative value, just get rid of the negative. Go ahead.
What'd you get for E-trans? Non?
E transmitted is right here. Let me put it down.
So on your solutions, you got 8.6 times 10 to the negative 4.
No, not
He fixed
anymore.
it.
I fixed it. That wasn't multiplied by 10. I'm sorry. There were a few things that were jimmied up, but Thomas Short was the first to mention it, but then other people saw it. And if you refresh your screen, if you're looking at a screen right now, you should be able to resync it, I think. You should see it.
Okay.
But do you understand why? Because when we do shielding effect, well, I'm sorry, for this you're talking about. This right here, I didn't put the 10 in the transmitted.
The 10?
The 10 incidence field strength is 10 volts.
Okay.
That was my problem. I think that was it. All right. Now, for shielding effectiveness, you do not need the field quantity, the E field strength. You could use it if you wanted. But shielding effectiveness is 20 times the log of E incident magnitude of this over E transmitted. But because E transmitted is related to E incident, it's really 20 times the log of simply magnitude of 1 over tau 1, tau 2, exp to the minus alpha d. And that's it. That's it. And I don't know what it is, but I think it's 60.9 or something.
Yep.
61.
And that's it. Now, it doesn't matter how these kind of problems can have so many things. Suppose I want you to calculate the thickness of the shield. It'll give 80 dB of attenuation. Then what do? Well, you start over here, right? You got 80 dB. You know, these two things just have to do with what? The material parameters, not the thickness. Theirs are the thicknesses, so you solve for that exponential e to the exp to the minus alpha d, right? And then you take the log of both sides and find alpha. Y'all follow me on that? So it's always one of these things, given any number of knowns, you can get the unknown just by reverse engineering. Okay, yeah.
Where's the D come from? Like
D
that?
is the thickness.
The thickness.
That's all it is.
Will we ever encounter a shield that's not a good conductor?
Oh, boy.
Uh-oh.
Well, I'm gonna level with you. One problem with shielding in general, this we cover in EMC, frequency ranges. When you get transient signatures, when you have these impulse things where the frequencies that are contained are very large, for some of those frequencies, the shield looks like a very good conductor, but for the very low frequency, it may not. And that's where you have to break the problem into segments to solve it. But that's a little further down the road. Okay, would you all spread out? How about first? No,